Atkins Civil 3D video series, Storm 1, Storm-Based Drawing. This video illustrates A. Update storm-based drawing, B. Pipe network storm parts list, C. Storm default settings, D. Structure and pipes numbering system, E. Comment on storm sanitary analysis, SSA, and F. Storm layer colors for source drawing. The current drawing is a storm improvement-based drawing that was created using procedures set forth in video EX1A. The sewer improvement objects were incorporated into the project-based drawing using the procedures set forth in video reference sewer, and via XREF are shown in the current storm improvement drawing. All Civil 3D drainage objects should be created on the storm improvement drawing. Check that the pipe network catalog has been set to US Imperial for pipes and structures. A home ribbon, create design panel, down arrow, set pipe network catalog. Both storm and sewer uses the same catalog. Pipe US Imperial, structures US Imperial, OK. Information on the part catalog is illustrated in videos Sewer 1A, Sewer Part Catalog. Check available storm parts list, settings tab, expand pipe network, expand parts list, C storm and EX storm are available. The difference between the pipes and structures in the various storm parts lists is associated with the styles column. Right-click C storm, edit, expand RC pipe. The style for C storm parts list is C storm. In addition to the C storm pipe style, EX storm and EX storm demo pipe styles are also available. The line work is bold for C storm and thinner for EX storm. In order for the pipes and structures to have the desired style, the correct parts list must be used in the initial creation of the pipe network. Check available types and sizes of pipes and structures. Pipe, reinforced concrete pipe, and reinforced concrete boxes are available. For the reinforced concrete pipe, the various diameter reinforced concrete box, the various width and height sizes are shown. For structures, there are null structures, reinforced concrete junction box, reinforced concrete head wall box inlet, reinforced concrete head wall 0-degree wing wall, reinforced concrete head wall 30-degree wing wall, concrete flared in section, and curb inlet. Due to the relative large size of drainage pipe, structures are generally rectangular in shape. Curb inlets and junction boxes have the same sizes and look the same in plan and profile. The reason for the different part types is that the part name is used in the label. Atkins uses length and width in the part size. There's a curb inlet that is 36 inches long and 72 inches wide, and there's also a curb inlet 72 inches long by 36 inches wide. The length is parallel with the station and the width is perpendicular to the station. To add a pipe, right-click C storm, add parts family. These are the various types of pipes that are available. The RC pipe and the RC box are not listed because they're already selected. Add HDPE pipe, place check mark, OK. Right-click the type, add part size. You can add individual sizes or use the Add All Size column to select all the diameter and thicknesses that are available. OK. Check the Style column. They're inserted as existing sewer. We're going to change the style to C Storm, which is the name of the parts list. OK. Apply. OK. Storm defaults are initially set for existing storm since they are the first to be created. Tool space, settings, right-click the drawing name, edit drawing settings, object layers, pipe, existing storm, pipe labeling, existing storm text, pipe and structure table, existing storm text, pipe network section, existing storm, pipe structure profile, existing storm, structure, existing storm, structure labeling, existing storm text. OK. Right-click pipe network, edit feature settings, default styles, default name format, structure name template is S, existing is 001, starting number 1, pipe name template, P next counter, number style 001, starting number 1, default rules, pipe network defaults, storm sewers migration defaults, default profile label placement, default section label placement. Okay. It generally does not matter what the number of the structure or pipe is when working only in Civil 3D. The number becomes more significant when transporting the pipe network data to Storm Sanitary Analysis, SSA. In such cases, it is recommended that structures be numbered starting with the lowest number for the upstream structure and proceeding downstream, with the downstream pipe having the same number as the upstream structure. When a structure is encountered that has a branch pipe connection thereto, the structure itself would not be initially numbered. The numbering would continue from the most upstream structure of the branch and proceed downstream to the main run connecting structure, at which time the structure would be numbered. The numbering would then proceed downstream along the main pipe run. A downstream structure would always have a higher number than an upstream structure, whether along a main or branch run. The entire pipe network may initially be laid out in a single pipe network group, ignoring the number that is assigned to the pipe or structure, and modify the number at a later date if desired. When setting up the pipe network for transporting to SSA, the structure and pipe numbers can easily be changed in Civil 3D at that time. The changes need to be made, however, prior to creating the data shortcut that will be used to transport the pipe network data to the drawing map, subsequently to SSA. It makes things a lot easier to have the same number in Civil 3D, drainage map, and SSA when checking or changing the elevations of pipes and structures. For some unknown reason, a maximum number of 27 catchments can be transported from Civil 3D to SSA at the same time without creating significant errors. This may change in future releases of Civil 3D. Due to the limitation of transporting a maximum number of 27 catchments, it is recommended that pipe network group be created in a manner to comply with this maximum number. I personally only use SSA for determining the size of the catchment area, the rainfall pass, and the time of travel. I have found that SSA to be cumbersome and time-consuming in the hydrology and hydraulic analysis of a storm drain system. This may change in future releases of Civil 3D. In the majority of cases, I use a spreadsheet I created for the hydrology analysis using the rationale method Q equals CIA. I have developed equations using sigma plot for the rainfall intensity duration frequency IDF curves and a procedure for converting the Soil Conservation Service curve number to the rationale C, which are included in the spreadsheet. I also use a spreadsheet I created for the hydraulic analysis of a storm drain system. I start from downstream with a known or assumed hydraulic gradient at the pipe soffit elevation. I proceed upstream computing the hydraulic and energy gradient at each upstream structure. In a huge majority of the cases, it is immaterial as to the actual flow characteristics within a pipe. The only concern is whether the size of a pipe is adequate to handle the design flow. As such, I make my hydraulic calculations simple by assuming full pipe flow. If the computed full flow hydraulic grade line for the outlet pipe at the upstream structure is less than the soffit elevation, I use inlet control and critical flow for computing the hydraulic grade at that location. If the hydraulic gradient in the structure is less than the soffit elevation of the inlet pipe, I use the soffit elevation as a hydraulic gradient for the upstream calculations in the pipe. The Layer Manager is currently open and shows the colors as recommended by Atkins for the storm objects created in the Storm Improvement source drawing for the C-Storm layers and for the EX storm layers. This video is a part of the Civil 3D video series created by Gerald Atkins of Atkins Engineering. Visit www.atkengr.com for instruction manuals, tutorial drawings, template drawings, and Civil 3D videos.